everybody. So now we're going to talk about a very fundamental theorem that relates homomorphisms, normal subgroups, and factor groups all together. And it takes a lot of sort of mental effort to sort of understand what the theorem says, but the proof is what in mathematics we would call abstract nonsense. In other words, by the time you make all the definitions and state everything properly, then the proof itself becomes very straightforward. So we're going to look at some examples and try to kind of build our way up to this, and then at the end of this, look at the proof. This way of thinking about things, I think, goes back to work of Emmy Noether, who was really one of the absolutely towering figures in the creation of the subject we call abstract algebra. She is also one of the few women who were able to overcome the kind of incredible levels of sexism and also anti-Semitism in the academic establishment, especially in Germany, to achieve a professorship and make get her work published and make a huge impact. She spent the end of her life in Bryn Mawr in Pennsylvania at the college there after escaping from Nazi Germany. But this work, which is related to the first isomorphism theorem, is usually traced back to a paper that she wrote in 1927. So let's dedicate this to Emmy Noether. So we'll see where we stand. So before we can talk about the theorem, the isomorphism theorem, or the first isomorphism theorem, I'm not going to talk about the second and third unless I absolutely have to. We need to introduce something called the canonical or the natural homomorphism. So this is just putting together some things that we've already done. So suppose we have a group, G, and a subgroup, H of G, which is normal. So in the case where we have a normal subgroup, we've seen that you can construct the factor group, G mod H. And remember what G mod H is. Its elements are the cosets, the left cosets, GH. And the group law is that you multiply cosets in the way you would hope to be able to multiply them, which is you just multiply their representatives. But it's crucial that H be normal in order for this to make sense. Otherwise, it wouldn't be independent of the choice of representatives. And the natural or the canonical homomorphism from G to G mod H is just the map which takes an element G and sends it to its coset representative GH. So phi of G is GH. And this is a homomorphism, and it's more or less a homomorphism for the reason I just wrote here, right? Phi of G1, G2 is G1, G2H, which is G1H, G2H, which is phi of G1, phi of G2. So it is a homomorphism. And maybe we take 1 second and just to ask, what is its kernel? So the kernel of this map phi is the collection of G such that phi of G is the identity of this group. But the identity of this group is the coset H. So in other words, it's the collection of elements G such that the coset GH is equal to H. And by the proposition 6.3 that everybody sweated over, this is precisely the G and H. The condition is just that G and H. G has to be an H. So in other words, the kernel of phi is H. So here we've constructed a homomorphism. We started with a normal subgroup. We've constructed a homomorphism which has that normal subgroup as its kernel. And remember I said that homomorphisms and normal subgroups go together. This is why. So you can take a normal subgroup, take the homomorphism to the factor group, you get a homomorphism which has that normal subgroup as its kernel. And conversely, take any homomorphism and you take its kernel, you get a normal subgroup. Just to sort of make this a little bit more concrete in some examples that I'm going to come back to in this discussion, what about so in the case of Z mod NZ, here let's suppose that n is it could be 0, but it's less interesting. So let's suppose n is bigger than or equal to 1. So what is this map? Well, it's the map which takes an integer a to the coset a plus nz. And we've seen that the cosets a plus nz are the congruence classes mod n. So the natural map in this case, or the canonical homomorphism from z to z mod nz, is the map which takes an integer and reduces it mod n. It assigns to it the coset a plus nz. And that map is onto z mod nz. What about the case where we look at the alternating group and the permutation group? So what's the natural map there? Well, here we're sending a permutation to the coset of the alternating group corresponding to that permutation. And remember that we know that there are only two cosets of the alternating group. So an consists of the even permutations. And there's just one coset tau an, which is the collection of odd permutations, where tau is any odd permutation. Could be a transposition. So this map, the natural map, takes an element, a permutation, to either the identity coset, which means it's even, or the non-identity coset of an, which means it's odd. And so this map is really the one we looked at before. If we identify the coset an with 0 in Z2, and the coset that's not an with 1 in Z2, then the natural homomorphism is the one that takes an even permutation to 0 and an odd permutation to 1. And in the case of GL2R, we have the normal subgroup SL2R. And in the section on cosets, we worked out that the cosets of this GL2R mod SL2R correspond to the multiplicative group of real numbers. Basically, the coset GSL2R consists of the matrices, let's call them H, whose determinant is equal to the determinant of G. Because when you multiply G by a matrix of determinant 1, it still has the same determinant. And if you have two matrices with the same determinant, then let's say X and Y, then XY inverse will have determinant 1. So again, if you go back to proposition 6.3, it's easy to prove this. Well, possible to prove it anyway. And so, but on the other hand, we know that we also have this map which goes from here to here, which is the determinant. And so the cosets GL2R mod SL2R correspond to the determinants. And this is therefore, this isomorphism here between GL2R and SL2 and mod SL2R and R star is a way of saying that, that the determinants of matrices, 2 by 2 matrices, are elements of R star. So it's good to keep these three examples in mind. Now let's take a look at the first isomorphism theorem. And as I said, it's a bit of a brain buster. So we'll start with the hypotheses. So the hypotheses are, first of all, we have a homomorphism of groups. So I'm going to have, it's probably best to refer to this diagram, which I took from the book. It's a standard diagram for explaining this theorem. So we have a homomorphism from G to H. And like any homomorphism, that homomorphism has a kernel, K, and it need not be bijective, so its image is psi of G is just a subgroup of H. So even though G maps to H, it may not hit all of H, it only might hit a subgroup of H. So psi of G is the image of G in H. And what the isomorphism theorem says is that you can make this map, this homomorphism, in two steps. First, you take the natural homomorphism from G to G mod K, where K is the kernel of phi. And having done that, the resulting group is isomorphic to the image of G in H. And I give here the reference to the work of Noether that I was talking about, where this idea is first presented. It's in this slightly different context, but the ideas are exactly the same. Okay, how are we supposed to make sense of this result? Well, there's different ways of thinking about it. One way to think about it is to give a homomorphism from G to H, you can always break this up into two steps. First, you go through the natural map to G mod K, where K is the kernel of, this is phi, where K is the kernel of phi. And second, the image of the homomorphism, I guess we call this psi and this phi, kernel of psi. The image of this homomorphism psi is then actually isomorphic to this quotient group G mod K. So the image of any homomorphism from G to H, puts a copy of a quotient group of G inside H. The image of a homomorphism is isomorphic to a quotient of G. So if you've got a group G and you want to take a homomorphism to H, the only way that can happen is if some quotient group of G is isomorphic to some subgroup of H. Okay, well, maybe it helps to look at some examples. So go back to the examples we looked at before, but now let's look just at the homomorphism. So here the homomorphism is the one that I talked about earlier, where phi of sigma is 0 if sigma is even, phi of sigma is 1 if sigma is odd. The kernel of phi is the group AN. If we draw the picture for the first isomorphism theorem, which I would encourage you to do in these situations, in which case I'm going to call this psi, which is not what I called it before, but it's what it's called in the diagram. Kernel of phi is what we called K. And what this is saying is that the map psi, which I've described here, that takes the sign of a permutation, corresponds to an isomorphism between Sn mod An and the image of psi. But the image of psi is all of Z2. There are both even and odd permutations. So what we're saying here is that because there's this homomorphism, the sign character, the quotient of Sn by the kernel of the sign character is isomorphic to Z2. And this is more or less the picture that we had before. So you can think of computing the parity of a permutation as taking the coset of An that it generates and looking to see whether that's 0 or 1. Let's look at another example. Back to the determinant. So in this picture, we have GL2R maps by psi, which in this case is the determinant map, to R star. The kernel of this is SL2R, the matrices of determinant 1. So the map, which is the determinant, can be obtained by first mapping to the quotient group, and then remember that this map here is onto. So we, in fact, psi of G is R star because every possible determinant occurs. So therefore, there's an isomorphism between GL2R and SL2R. So one way you can use this theorem in lots of different ways. One thing that you can use this theorem for is that it tells you that this quotient group must be isomorphic to R star. Because if the determinant map, the determinant map is onto R star, by the isomorphism theorem, you have to be able to first go to GL2R mod SL2R, and then this has to be an isomorphism onto the image. But the image is all of R star because it's onto. So the calculation that we did earlier, where we showed that GL2R mod SL2R corresponds to the determinants, comes for free out of this isomorphism theorem. So let's look now at this example. Here we have a case where the map is not in general surjective. So let's call this psi, because that's what it's called in the statement of the theorem. So here our group G is Z, and G is any group, but we have an element G in it. So if you want to make this more concrete, you could say that G was the symmetric group, for example, and little g was some permutation. It doesn't matter what. And the map is psi of G equals G to the n. So what is the kernel of psi? The kernel of psi is the collection of integers n such that G to the n is equal to the identity. Because to be in the kernel is to be in a situation which you map to the identity. But we know a lot about this. We've studied orders of elements, and we know that G to the n is equal to the identity if and only if the order of n order of G divides n, or G has infinite order. Let's assume first that G has finite order. And if that's the case, it means that the n's such that G to the n is equal to the identity are precisely the multiples of the order of G. So the kernel of psi is the order of G times Z. And what does the isomorphism theorem say in that case? Oh, and maybe we should do one other thing. What is the image of psi? Well, we looked at this before. It's the collection of powers, integer powers of G. And that's what we were calling the cyclic subgroup generated by G. So our picture now looks like this. We have Z goes to the cyclic subgroup generated by G, which is a subgroup of G. The kernel is order of G, Z. The map here is psi. It's this map G to the n. The isomorphism theorem says you can first go to Z modulo the order of GZ. So this is a Z mod NZ, where n is the order of G. It's a finite cyclic group. And that is then isomorphic to the cyclic subgroup generated by G in the group big G. In other words, we've shown here that the cyclic subgroup generated by G is isomorphic to Z modulo the order of G, Z. And that shouldn't be too surprising. I mean, the isomorphism is just that you send n to G to the n. And if you happen to be in the order of G, a multiple of the order of G, then you go to the identity. But that's what the isomorphism theorem says in this particular case. And maybe we can look at one more. Suppose we could make this even more concrete. Let's look at Z mod 12Z. So we're taking integers mod 12, and then we decide to reduce them mod 3. So this is a homomorphism, and if we were going to write it in terms of congruence classes, we're sending A plus 12Z to A plus 3Z. Take the number mod 12 and reduce it mod 3. What does the isomorphism theorem say? Well, what's the kernel of this map? If you're a number mod 12 and you become 0 when you reduce it mod 3, that means you're a multiple of 3, right? So the kernel of this map is 3Z mod 12Z, which is a subset of Z mod 12Z. And this is the kernel of psi. And that's telling us that Z mod 12Z mod 3Z mod 12Z is isomorphic to Z mod 3Z. And in some sense, it's saying you can sort of cancel out the Z mod 12Zs, although I don't necessarily recommend doing that. But it shows you that you can interpret this Z mod 3Z as a quotient group of Z mod 12Z. It's not just a quotient group of Z, but it's a quotient group of Z mod 12Z as well. Okay. Now, let's try to prove this isomorphism theorem. And to do that, we have to explain how to get this map eta, right? Because phi is given, it's the natural map, and psi is given, and g is given, and h is given, and k is given. The only thing in this thing which we don't know is eta. And eta has to take a coset from g mod k and map it to an element of h. And the condition is supposed to be that this diagram commutes. In other words, we need to have the equation psi of g has to equal eta phi of g. That's the condition. So let's define here. As I said, the proof looked at in the right way is kind of automatic once you have all the definitions straight. And so the definition that we're going to make is we're going to define eta of a coset, gk, to be psi of g. In other words, you take your coset, you find a representative of it, and you apply psi to that. And that, I mean, that's an element of h. The complication here is that it's, first of all, what do we want to be true? First of all, this map had better make sense. And the problem there is that there's more than one representative of the coset gk, right? It has to be, so let's check that this eta works. So first of all, is it well defined? For that, we need to know that eta of gk has to equal eta of g prime k if gk equals g prime k. Well, if gk equals g prime k, then that's if and only if, by the famous proposition 6.3 that everybody proved in the homework, that g equals g prime k for some k and k. And if that's the case, then we would have eta of gk is psi of g, and eta of g prime k is psi of g prime, but psi of g is psi of g prime k, and psi is a homomorphism, so that's psi of g prime psi of k, but psi of k is the identity, because k is in the kernel of psi. And the kernel of psi means that psi of k is the identity. So this function eta at least is well defined. Is it an isomorphism? Well, if it's going to be an isomorphism, it has to be a homomorphism, and it has to be bijective. So let's check to see if it's a homomorphism. Well, eta of g1k, g2k is, on the one hand, eta of g1, g2k, which is by definition psi of g1, g2, but eta of g1k, eta of g2k is psi of g1, psi of g2, but psi is a homomorphism, so these are equal. And then we need to check that it's bijective. So let's check that it's injective. So its injective mean would be, we assume that eta of G1k equals eta of G2k. Well, that means psi of G1 equals psi of G2. And that means that psi of G1, psi of G2 inverse is the identity. And that means that psi of G1, G2 inverse is equal to the identity. And that means that G1, G2 inverse is in the kernel of psi, which by definition is K. But if G1, G2 inverse is in K, that implies, by that same proposition about cosets, that G1K equals G2K. So if eta of G1K equals eta of G2K, then G1K equals G2K, and so the map is injective. And is it surjective? Well, that's a little bit easier because we need to show that if, let's say H is in psi of G, we know that H is psi of G for some G. And if H is psi of G for some G, that means that eta of GK is psi of G is H. So H is in the image of this map. So when you put all this together, you see that you can find this eta, and then it has to have all of the claimed properties. So that's the story of the first isomorphism theorem, or the isomorphism theorem. And as I said, I think we're going to table what the book calls the second and third isomorphism theorems in case a situation comes up where we actually want to use them.